If metadata filters are hurting your RAG results, I will show Prefilter versus Postfilter on a toy example, and how to design metadata that stays reliable. You run retrieval augmented generation, and you expect filters to steer retrieval to the right domain. Instead, you get wrong or empty answers. By the end, you will know which filter strategy to pick and how to make metadata robust so the model actually sees the right documents. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Metadata filters live inside retrieval augmented generation pipelines to narrow results by attributes like department, product, or version. People use them when a model must only see domain-specific text. Success means the generator gets relevant context without exposing irrelevant documents. The practical pain is subtle. Filters can remove good documents or silently hide recall. That increases hallucination risk. The choice between pre-filter and post-filter matters for accuracy and latency. At a high level, pre-filter applies the metadata restriction before you search. Post-filter applies it after you have retrieved candidates. Pre-filter reduces the search space and can be fast. Post-filter preserves recall by filtering after a wider search, but needs a bigger candidate pool. The mini example uses a small corpus of documents that include text and a metadata field called department. Some entries have inconsistent casing, like sales versus sales, to show a real pitfall. We will build a tiny corpus, rank by simple lexical match, and compare pre-filter and post-filter behavior under top K truncation. Then, we will widen the post-filter candidate pool to show recovery, show how casing breaks filters, and fix it by normalizing metadata. The code feels simple because it only uses a lexical ranker and a metadata field, so you can map the ideas to any vector or ANN setup. Now, we build the tiny corpus and a simple lexical ranker. This snippet builds a tiny corpus and lexical ranker for a baseline. It creates a handful of documents where each document has a text field and a department metadata field. The lexical ranker is a simple text match scorer that counts overlap between a query and document text. The code shows how documents are stored and how the ranker returns a scored list sorted from highest to lowest score. The ranker is our baseline, so later comparisons isolate the effect of metadata filtering rather than vector math. Next, we will compare pre-filter and post-filter behavior under top K. This snippet contrasts pre-filter and post-filter under top K truncation. It runs two flows on the same query. The pre-filter flow first filters documents by department and then applies the lexical ranker to that smaller set. The post-filter flow ranks across all documents and keeps the top K candidates, then discards those whose metadata does not match. You can see the practical difference. Pre-filter never ranks a document that was excluded by metadata, while post-filter may rank a relevant but lower scoring document that would have been visible if the candidate pool had been larger. The key parameter here is top K, which controls how many candidates get passed along to the filter. Now, we will widen the candidate pool used for post-filter to show recovery of missed results. This snippet widens candidate K for post-filter to recover recall. It reruns the post-filter flow with a larger candidate pool before applying the metadata check. The idea is simple. A relevant document might not be in the original top K because lexical score is lower. By expanding the candidate pool, you give the post-filter a chance to include that document and restore recall. The code highlights the trade-off. Increasing candidate pool size raises the chance of recovering relevant documents, but also increases latency and the amount of context the generator must handle. Tune the pool size to balance recall and cost. Next, we will demonstrate a metadata formatting pitfall. This snippet exposes recall loss from inconsistent metadata casing. It shows documents where the department field appears as both sales and sales. The filter checks may be case sensitive, so a pre-filter or post-filter that compares values literally can exclude matching documents. The snippet runs the same query and shows that filters miss documents only because values do not match exactly. The practical lesson is that metadata inconsistencies create silent failures. The retrieval scores are fine, but the filter logic throws documents away. Finally, we will normalize metadata to fix the problem. This snippet normalizes metadata to restore stable, accurate retrieval. It adds a normalization step that lowercases or canonicalizes the department field at index time and query time. After normalization, the same filter expressions match reliably, so both pre-filter and post-filter flows behave as expected. The code shows that the normalization is cheap and happens once at ingestion, and that fixing metadata semantics removes a whole class of recall bugs without changing the ranking model. In a real project, this toy maps directly. Replace the lexical ranker with an embedding index or FAIS. Replace department with product ID or release tag. Normalization and candidate pool tuning are the same ideas at scale. 3 crisp takeaways. What it is: a comparison of applying metadata filters before retrieval versus after retrieval. When to use it: use pre-filter when metadata is authoritative and consistently formatted, and you need low latency. One caveat: if metadata is inconsistent or your top K is small, pre-filter can silently lose relevant documents. Next step: increase the post-filter candidate pool size and measure recall and latency to find the best trade-off for your workload. If practical AI engineering helps, subscribe and watch the AI engineering videos.